There's a room under the Brooklyn Tower big enough to swallow a city block, sealed shut and pumped full of pressurized air so men could dig out the riverbed underneath without the whole thing flooding. Nobody had a bulldozer or a diesel engine for any of this. Construction started in 1869, before cars existed, so every tool on site ran on steam or straight muscle. And it still ended up taller and longer than any suspension bridge built before it. Some of the steel holding up the cables today never should have passed inspection in the first place, and the contractor who sold it barely faced any consequences for it. Getting those cables into position took a machine that crossed back and forth over the river thousands of times, laying down more than 14,000 miles of wire, one strand at a time. I dug through construction reports, engineering logs, and period trade journals, and used advanced AI to reconstruct exactly what tools, machines, and techniques actually built this bridge. 14 years, and not one piece of modern machinery ever touched it. By the 1860s, roughly a quarter of all suspension bridges built in the 19th century had failed outright, torn apart by wind or collapsed under their own movement. Engineer John Roebling had never lost one of his own designs, having already built working suspension spans over the Niagara and Ohio rivers. One of the most infamous failures, the Wheeling Suspension Bridge in Virginia, tore itself apart in 1854, when ordinary wind set its unstiffened deck oscillating until the whole structure twisted loose and collapsed into the river below. Spanning the East River meant a main span of nearly 1,600 feet, longer than any suspension bridge attempted before it, over water too deep and too busy with ship traffic for a temporary support structure underneath. Roebling's answer combined three separate systems most engineers used alone: parabolic suspension cables to carry the vertical load, a web of diagonal stay cables running from the tower tops down to the roadway to resist wind, and a stiffened, open truss deck that let wind pass through the structure instead of slamming against it. The diagonal stays alone used enough additional wire rope to visually resemble a giant spider web radiating down from each tower, a look that turned out to be as functional as it was distinctive. He didn't trust the math of his own era to get the margins right. Roebling designed the entire structure to be 6 to 8 times stronger than his calculations said it needed to be, an overbuilt safety factor that had no real precedent at this scale. Nobody had wind tunnels or aerodynamic modeling in 1869. Every one of these decisions came from watching earlier bridges fail and guessing, carefully, at what had gone wrong. Roebling had already used a version of this same stay cable system on his Cincinnati-Covington Bridge in 1867, a smaller rehearsal for the East River crossing that convinced him the approach could scale up. None of that mattered yet. The real test was still underwater. Before either tower could rise, engineers needed a way to reach solid ground underneath a tidal river without draining it first. The solution was a caisson, essentially a massive upside-down wooden box, open at the bottom and sealed everywhere else. Workers built the Brooklyn caisson on land first, a timber structure 168 feet long and 102 feet wide, with a roof 15 feet thick, made of stacked, bolted yellow pine, all of it sheathed in iron plating to keep the wood from rotting once submerged. Crews launched the finished caisson like a ship, floated it into position, then lowered it by stacking granite masonry on top in careful stages so it sank evenly instead of tipping. A heavy iron shoe reinforced the bottom edge, angled like a blade to cut through mud and gravel as it descended, while timber partitions inside kept the sinking controlled rather than letting one corner drop faster than the rest. Quick pause. If this is the kind of history you want more of, subscribe so you don't miss the next one. And if you're finding this interesting, a light goes a long way. Compressed air, pumped down through iron pipes by steam-driven compressors on barges above, kept water and mud from flooding the sealed working chamber underneath as the caisson sank deeper. Losing that pressure even briefly risked letting river water and mud rush straight back into the chamber. I still find it wild that the very first step in building America's most famous bridge was constructing a giant sealed room, specifically so people could dig underneath a river without drowning. A fire actually broke out inside the Brooklyn caisson in December 1870. smoldering in the compressed air atmosphere for days before crews managed to flood sections of the chamber to put it out. An incident that forced engineers to seal the Brooklyn Foundation somewhat earlier than originally planned. Inside that sealed chamber, roughly 9.5 feet tall, workers dug by hand using picks, shovels, and short-handled tools suited to cramped, low-ceiling conditions. There was no mechanical excavation of any kind. Every bucket of mud, sand, and boulder came out through a water-filled shaft, hauled up by rope and pulley to barges waiting above. Access ran through airlocks, small chambers where workers adjusted to the pressure before entering or leaving. Air pressure at the deepest points reached roughly 35 pounds per square inch above normal, more than double what most human bodies had ever experienced. A shift inside the deepest sections rarely lasted an hour. Workers took to calling themselves sand hogs, a nickname that stuck to underground construction crews for generations. Why did anyone accept a job that involved digging underwater inside a pressurized wooden box lit by gas lamps? Pay, mostly, at wages well above typical labor rates, and the simple fact that nobody fully understood the risk yet. Workers surfacing too quickly from the pressurized chamber developed a condition doctors eventually named caisson disease, now known as decompression sickness. The Brooklyn caisson reached bedrock at 44.5 feet and stopped there. The Manhattan caisson kept going, hitting no solid bedrock at all. And Washington Roebling made the call to halt excavation at 78.5 feet on firm sand, rather than risk more men to the pressure at greater depth. Physicians on site initially blamed the cold, the damp air, or general overexertion, since nobody yet understood that dissolved nitrogen bubbling out of the bloodstream during rapid decompression was the actual cause. Washington Roebling's own time inside the caissons had already cost him. His decompression sickness left him largely bedridden from 1872 onward, barely able to leave the house overlooking the construction site. His wife, Emily Warren Roebling, stepped in, teaching herself calculus, cable mechanics, and materials science to manage a project she hadn't designed, running daily liaison between Washington and the contractors for the remaining 11 years of construction. When the bridge opened, she crossed it first. Once each caisson reached its final depth, crews filled the entire working chamber solid with brick piers and concrete, permanently converting the temporary digging tool into the tower's actual foundation. With solid foundations in place, the real stonework could begin. And it needed material from hundreds of miles away. How do you keep a 9-ton block of stone from cracking the instant a crane grabs hold of it? Granite for the towers came from the Bodwell Granite Company's quarry on Vinyl Haven Island, Maine, cut from the rock using drilled holes packed with expanding wedges rather than explosives, then squared by hand with pitching chisels. Some blocks weighed 9 tons or more before they ever left the quarry. Workers split each block along natural fracture lines in the stone, a technique quarrymen had refined over generations specifically to avoid wasting material or weakening a finished block with an uneven break. Finished stone traveled south by schooner, unloaded at the construction site, then hoisted using steam-powered engines running roughly 350 feet of 1.5-inch steel rope through a system of derricks mounted directly on the rising towers. Rail track laid alongside the site let crews roll each block straight from the waterfront to whichever tower needed it next. You don't grip it, you lock into it. Each block needed a Lewis, a metal fitting fitted into a drilled mortise in the stone so cranes could lift it from the inside without ever touching, let alone cracking, the finished edges. Limestone, quarried separately in upstate New York, formed the lower courses below the waterline, chosen because it held up better against constant moisture than the granite used above it. Blacksmiths worked on site continuously, sharpening chisels and drill bits dulled by constant contact with the stone. I get a kick out of the fact that a 9-ton block of Maine granite crossed hundreds of miles of open ocean just to get lifted the final 250 feet by a steam engine and a rope. The two towers eventually rose 276 feet above the water, containing more than 85,000 cubic yards of stone, all stacked and mortared by hand over roughly 6 years. Each incorporated a pair of pointed Gothic arches, cut stone by stone to a curve rechecked constantly as the courses climbed. On shore, Matching limestone anchorages rose alongside them. Trapezoidal blocks roughly 120 feet deep, engineered to bear the full pulling force of the finished cables without shifting. Even as the towers climbed, engineers had already started the next problem. How do you make a cable strong enough to hold up a bridge this size when nobody manufactures one that large in a single piece? You don't build the cable first, you build it in place, one wire at a time, using a temporary footbridge strung between the towers specifically so workers could reach the middle of the span while construction was still underway. A traveling wheel, powered by a 30-horsepower steam hoisting engine on the ground, carried a continuous loop of wire back and forth across the river, unspooling one strand with every pass. Each finished cable eventually contained 5,434 individual steel wires, grouped into 19 strands of 286 wires each, made from crucible steel, rather than the untested Bessemer steel some contractors were pushing at the time. Engineers calculated the exact sag each wire needed to carry its share of the load evenly, then adjusted tension by hand as each new strand went up, checking the math against the physical cable constantly, rather than trusting a single calculation done in advance. Workers rode small wooden buggies alongside the moving wire, in open air hundreds of feet above the water, lashing the strands together and checking tension by feel as much as by instrument. Every so often, a gust caught a buggy mid-span and sent it swinging hard enough to nearly throw its rider, and crews learned to anchor themselves to the cable strands directly whenever the wind picked up over open water. Once a cable's strands were all in place, a separate wrapping machine spiraled soft wire tightly around the finished bundle, compressing it into a smooth cylinder and sealing it against weather with a coat of raw linseed oil and lead paint. The wrapping machine itself was one of Roebling's own inventions, a rotating iron clamp that squeezed the loose bundle of wires into a perfect cylinder before winding it tight. The whole spinning process for all 4 cables ran from June 1877 to October 1878. 16 months of near constant work suspended above open water with nothing but a temporary footbridge and a steel cable underneath. Every one of those thousands of wires was supposed to pass the same strength test before it ever reached the river. Not all of them did. Partway through that process, engineers discovered the wire itself wasn't what it claimed to be. A contractor named J. Lloyd Hay had won the contract to supply the cable wire, and by mid-1877, Chief Engineer Washington Roebling suspected Hay was quietly swapping in wire that failed the mill's own strength tests. By July 1878, the evidence was undeniable. Hay had substituted rejected wire and pocketed the difference, and some of it had already been spun into the finished cables. Roebling had insisted on testing every ring of wire before it left the mill, a level of scrutiny driven by the fact that Hay's reputation had worried him from the start. Pulling the compromised wire back out would have meant unraveling months of finished work and possibly bankrupting the project outright. Roebling did the math instead. He calculated that even with roughly 150 to 220 tons of substandard wire already inside the cables, the bridge's safety margin only dropped from 6 times to approximately 5, still well above what the structure actually needed to carry traffic safely. Personally, I think Roebling's response to that fraud is more impressive than the fraud itself. Instead of tearing the cables apart, he forced Hay to supply 150 extra wires per cable for free, then kept building. The final cables measured nearly 16 inches in diameter and were tested to hold well beyond the bridge's expected load, fraud and all. With the towers standing and the cables spun, workers still had to hang an entire roadway underneath, one piece at a time. Steel suspender ropes dropped down from the main cables at regular intervals, each one anchored to a steel floor truss assembled section by section across the span. Crews riveted the trusswork together by hand, heating each rivet red-hot in a portable forge before hammering it into place, since welding as a structural technique didn't exist yet either. Crews assembled the trusswork outward from each tower and anchorage simultaneously, working toward the center of the span where the 2 halves would eventually meet and lock together at mid-river. Getting those two halves to actually meet required constant resurveying as the ironwork crept outward from opposite shores, since even a small error compounded over 1,600 feet would have left a visible gap or forced an ugly splice at the center. When the sections finally connected in 1878, surveyors measured the alignment within a fraction of an inch. The finished deck carried 5 lanes side by side, 2 roadways, 2 rail tracks, and a raised promenade down the center, all resting on that same hand-riveted trusswork. The finished roadway sat 135 feet above the water at its center, high enough to let full-masted ships pass underneath without lowering a single sail. Workers coated every exposed piece of ironwork in protective paint as it went up, since untreated steel exposed to salt air over the East River would have started rusting within a single season. By the time construction wrapped in the spring of 1883, the project had cost roughly $15 million and the lives of at least 27 workers, most through construction accidents or the still poorly understood effects of decompression sickness. The bridge opened to the public on May 24, 1883, 14 years after the first caisson touched the riverbed, and more than 150,000 people crossed it that first day, walking over a structure built almost entirely by hand, steam, and a stubborn refusal to trust anyone's math without triple-checking it first. It still amazes me that every one of those first crossers walked calmly over cables quietly carrying someone else's fraud inside them, holding just fine anyway. None of the machines that raised this bridge would look out of place in a museum today. Steam derricks, hand drills, rope and pulley hoists. What actually held it together wasn't one invention. It was Roebling's refusal to trust a single safety margin, and a wire fraud recovery built on recalculated arithmetic instead of panic. The bridge still carries roughly 100,000 vehicles and pedestrians a day, resting on the same foundations poured into those original caissons more than 150 years ago.
Hit subscribe for more machine-by-machine breakdowns and drop your next request in the comments.